I want to do a quick video just to go over how to do these approximations, give another example how to look at these things graphically and numerically. We know we've got some analytical rules coming and we're going to keep building those out, but first let's try and look at how we're going to read a graph of a limit, and then we'll do some numerical approximations. These are all approximations, and we'll try and remember that the goal is that we're trying to find some pattern in our y values, some output that it looks like we're getting close to, where we're getting close to that y value as our x values get close to whatever number we're supposed to be getting close to. So let's start with a look at this thing graphically. Here's some random piecewise function that we came up with, and what I want to do is take a look at two different limits. We'll first take a look at the limit as x approaches -5 of this function, and then we'll take a look at what's going on around 2, and we'll see what's going on. So first, let's see if we can figure out here what's going on as x approaches -5. I'm going to take a look at the limit on the left first, and that means I'm going to pick an x value that's left of -5. I'll find my point on the graph. I'm going to follow my graph, and I'm going to try and see where my y values look like they're headed. Since, again, we're focusing on the y values, what we'll notice is that as our x value gets close to -5 on the left, our function outputs, the y values, look like they're going to 0. Similarly, on the right, we can pick some x value that's bigger than -5, maybe one right here, and we'll look at the point on our graph there, and then we'll follow our graph as our x values get closer and closer to -5. And again, we're going to try and figure out what our y values are doing. So here, as x gets close to -5 on the right, our function values again look like they're going to 0. Since we've got that the left side limit and the right side limit both look like they're pointing to the same y value, that's what our two-sided limit is. So in this case, we can say our two-sided limit is equal to 0 because the left and the right both point at the same spot. We'll take a look at what's going on around 2 in the same way. So first, we'll take a look at what's going on the left. If we go left of our x value of 2, a point on our graph would be like here, and we can follow our graph down, and you'll notice that it looks like we're pointing to this y value here at 3. So what that says is that the limit on the left of 2 for this function is going to be 3. And then again, we'll go ahead and grab a point on the right of 2, maybe somewhere over here, and we'll drag that point closer and closer to the x value of 2. And in this case, we'll notice that as x gets close to 2 from the right side, our function values are actually getting close to -1 here. Now, since the left side and the right side aren't the same thing, we can say the two-sided limit does not exist. I use D and E sometimes just to represent that. Graphically, what we're noticing then is for limits that do exist, like this one, see how the left side arrow and the right side arrow kind of point at each other? It looks like they're going to the same spot. That's one of the things that we'll notice. Here, our left side arrow and our right side arrow are pointing to different y values. So that's what's going to be giving away the fact that the two-sided limit doesn't exist. Don't get thrown off by this point down here. It doesn't actually mean anything for our limits. In this side, we're looking at what happens as x gets close to -5. We never actually look at what happens at the x value -5 itself. So sure, we've got something like f of -5 equals -3 in this case. And over here, we could say f of 2 is equal to -1. Because that's where our point is defined here. But it doesn't actually impact our limit statements at all. These are completely separate from our limits, and we shouldn't mix those up with what we've got going on there. So that's an example of how to read these things graphically. Let's do a numerical approximation. I've got a nice limit here that we can estimate numerically. What we're going to do, again, is try and figure out what's going on with a left-sided limit. We'll see what happens as we get close to 3 on the left for this function. And then we'll try and figure out a right-sided limit after that. We'll see what happens as x gets close to 3 on the right here. For these numerical approximations, what we're going to do is we're going to almost do the exact same thing. We're going to pick an x value on the left of 3. Maybe we'll pick something like 2. And then we're going to pick x values that are closer and closer and closer to 3. So maybe we'll say 2.9 is pretty close to 3. And then 2.99. And maybe we'll do one more. 2.999. And what we want to do is figure out what the square root of x plus 1 is. Grab your graphing calculator, or just a calculator in general, and we'll see if we can plug these in. This one's pretty easy. It's the square root of 2 plus 1. Oops, there we go. So that's the square root of 3, which is approximately, maybe I'll put the little approximate sign here. That's approximately 1.73. And then we've got the square root of 3.9, which is approximately 1.975. And if we keep plugging in these values, 2.99 now, we're going to get 1.9975. And then if we put in 2.999, we're going to get 1.99975. One more 9. There we go. As our answer. We can see pretty clearly what this pattern is. It looks like these y values are getting close to 2. So we might say that the limit on the left is equal to 2. On the right, we'll do the same thing. We'll go ahead and pick some x values, but now they're going to be close to 3, but a little bit bigger than 3. So maybe we'll start with 4, and then maybe we'll say 3.1, 3.01, 3.001. And we'll again plug these into our function, and we'll see what we get. Here we're going to get the square root of 5, which is approximately 2.236. Maybe I'll round that off to 2 decimal points and say this is approximately 2.24. And then if I put in 3.1, I'm going to get the square root of 4.1, which is going to be a little bit bigger than 2, 2.025. And then I'll put in 3.01, and I'm going to get 2.0025. And then I'll put in 3.001, but we can already see what's happening. I'm going to get 2.00025. And again, we'll notice that this look like they're going to 2. So we might say that the limit on the right is also 2. Since the left side limit and the right side limit are the same thing, we can say pretty confidently that our approximation of the two-sided limit is also 2. Now again, this is an approximation. This is not an actual perfect answer. This is just a very educated guess. And if we wanted to get a better guess, what we'd have to do is fill out a couple more of these test numbers here, just to get a more accurate idea of what's happening. My guess is that these 4 examples on each side of 3 are pretty convincing for you guys. We believe that the y values look like they're going to 2. But if we wanted a better approximation, you can always just do more examples. Anyways, that's what we mean when we're talking about reading these limits graphically, estimating them graphically, approximating them graphically, and then the same thing numerically, doing these numerical approximations by plugging in these test numbers. Hopefully that's relatively helpful. Thanks.